All right, next talk, Keonho will tell us about verifying crash consistency.
Hi all. Today I'm going to talk about our paper towards verifying crash consistency. This is a collaborative work with my colleague Conan and our advisor Brian Demsky. Ensuring crash consistency or implementing programs correctly in the presence of crash shows up in various contexts. Here we have two examples. On the left, we have persistent memory, which is a non-volatile memory that can replace traditional DRAM with only about 2 to 3 times higher latency while maintaining the content in the presence of crash. And on the right, we have CXL, a new open standard for pooling memory across a network via cache coherent links between machines, where each machine's failure is independent from each other, giving a partial crash model. Even if we use these hardware technologies that survive crashes, either fully or partially, we still face problems when designing crash-consistent data structures. First, in many failure scenarios, CPU cache is volatile, hence proper fence and flush operations are required by the users. If these operations are not specified, those cache flushes are done arbitrarily, which result in stores may not be persisted in the same order as they are executed. Also, even if the persistence order is ensured by the proper fence and flush operations, we still need to design data structure correctly in the presence of crash. We decompose the problem of implementing crash-consistent data structure into two parts. First, proper fence and flush insertion, and second, the correct design of the data structure, and our work mainly focuses on the second part. Let's first look at how we define crash consistency. Here's an abstract representation of concurrent program execution, where each line represents threads running operations. We assume partial crash model and say the crashes occur at these points asynchronously. The parts that are not executed due to the crash are indicated by the gray area. Our criteria for the crash consistency is all or nothing semantics, ensuring the atomicity of data structure operations. In other words, operation 2 finished before the crash and operation 3 has not started due to the crash. And we would like to make operations that are interrupted by the crash, operation 1 and 4 for instance, also acts as if they either finished or not started at all. So for instance, if the following execution where operation 1 and 2 are complete, while operation 4 has not started at all, is equivalent to the previous execution, then we say the execution follows all or nothing semantics. One programming paradigm to achieve all or nothing semantics is the idea of commit store, where there is exactly one point in each operation that logically stores the whole operation. If the implementation follows the commit store pattern, it trivially satisfies all or nothing semantics. For instance, if the red lines indicate the commit store points, then in this execution, operation 1 is logically complete, since its commit store is completed before the crash, and operation 4 is logically not started at all since its commit store is not applied. We wanted to help user to implement crash-consistent data structure following the commit store pattern by providing our language, CrashLang. Here's an overview of how CrashLang works. Users first write CrashLang source code, and if it passes our type system, then the backend compiler inserts proper fence and flush operations with some additional code injection to provide crash consistency, and it's finally transpiled to Rust code, and the output code is guaranteed to be crash consistent. As mentioned, we have decomposed the problem into two parts, where the type system ensures the correct design of crash consistent data structure, and the fence and flush insertion from the backend compiler ensures the correct persistent order. Let's start with a concrete example to illustrate some CrashLang features. Harris linked list is a lock-free data structure, which turns out to be a great example of showing the commit store pattern. The elements are stored in an ascending order, and the insertion and deletion methods traverse the list and find the correct spot to either insert or delete using compare and swap operation. Before getting into the example, we're noting that CrashLang is built upon the type system called lolcat, which is ensuring linear ownership of references. Hence, our language construct is similar to theirs. Here's an example run of insertion. Say element 2 and 5 already exist in the list with the sentinel nodes at each end, and insert of 4 is called. The insertion starts with allocating a new node and setting up the key. Then it traverses the list to get to the position for the insertion, indicated by the left and right pointers. The next pointer of the new node is set to the right, and the compare and swap on left.next to the new node is applied. If the cast succeeds, it completes the insertion of the new node. In the insertion, there are multiple steps of updating the global state consisting of multiple store operations, and it seems problematic if a crash occurs in the middle of these stores because the partial update of the insertion is applied to the global state, contradicting the all or nothing semantics. However, if a crash occurs before the cast of left.next is done, all previous updates are local to the current thread and invisible to other threads, and those stores will have no effect upon crash. And these stores become visible after the cast on the left.next is performed, which is logically committing the whole insertion operation. Hence, such cast serves as a commit store of the insert operation, and the rest of the stores that are invisible to other threads, we call them physically invisible stores. Our type system distinguishes these physically invisible stores by keeping track of the references that are exclusive to the current thread with the type called pristine. When a new node is created, the reference has a pristine type and keeps its pristineness until the cast of left.next points to it. And when a successful cast exposes the new node to other threads, this is when the new node reference loses its pristineness and becomes visible to other threads. Using this pristine types, any stores on pristine objects are physically invisible stores, and these stores will have no logical effect on a global view. Next is deletion. Again, we start with 2 elements, 2 and 5, and the delete of 5 is called. The correct position is found with the left and right pointers after traversal. Note that naively casting left.next to right.next result in an incorrect implementation, since right.next may be modified during the process. Hence, the deletion of an element is done in 2 steps. We first make sure that the right.next is immutable, then perform the cast that removes the right node. To do so, given a pointer address of right.next, we steal 1 bit from the address and use it as a mark bit, and this bit will be used as a logical indication of the safe cast for deletion. Back to the example, after finding the left and right positions, we first mark the bit atomically using compare and swap, marking the bit and making it immutable, and we say the pointer is fixed. Then the compare and swap is applied, which completes the deletion operation. Similar to the insertion case, we have multiple stores fixing the right.next pointer and cast of left.next. And if a crash occurs between fixing the pointer and the deletion cast, it seems like the implementation doesn't follow the all or nothing semantics, since the deletion is partially completed. The solution is to make such deletion cast to be every thread's duty. As mentioned, fixed pointer is used as a logical indication of a node deletion. Hence, if the current thread crashes before the deletion cast, and say if thread 2 notices this, it will perform this compare and swap instead, which effectively completes the crashed operation. And we say thread 2 helped the operation. In CrashLang, users can specify when and how these helping is done in the struct declaration using help signature, which will be explained in detail in a few slides. Hence, fixing the pointer, which is a logical indication of the deletion, is a commit store. And for the explicit deletion cast, we call it a helping action. CrashLang provides multiple features to support the helping action. First, to manipulate the mark bit of a pointer, CrashLang has 2 primitives, isStable and fix. isStable checks if the given pointer's mark bit is set, and fix marks the given pointer, making it immutable. Also, we allow users to annotate the fields to indicate when helping actions are necessary and how they are done. In the example, the next pointer in the node struct is annotated with a help type, which we call a helpable field, with an additional field in the angle bracket, which is called a condition field. Whenever a helpable field is accessed, if the corresponding condition field is fixed, a proper helping action of casting the helpable field to the fixed pointer address is generated using these annotation, which ensures helping action is done by any thread observing this condition. We have seen 2 examples of crash-consistent data structure implementation using a commit store pattern. Simply put, in a data structure operation, there is a commit store that logically commits the whole operation, and any other stores must have no logical effects. CrashLang type system identifies 3 kinds of stores that have no logical effects: physically invisible stores, helping action, and logically invisible stores. We didn't include the details of logically invisible stores due to a limited time, and it can be found in the main paper. We have implemented multiple data structures on CrashLang: stack, queue, linked list, binary search tree, and hash table. First, although we have a crash consistency proof, we empirically check the crash consistency of CrashLang data structure implementations. For each data structure, we first ran a concurrent execution of threads non-deterministically and injected partial crashes between every possible store operations with around 10,000 to 10 million elements. And as expected, our generated code has no crash consistency bugs. We also compared the performance of our data structure implementation with the handwritten versions and the benchmarks from Memento, where Memento is a type system with a user annotation guaranteeing crash consistency, which is similar to our approach. For each benchmark, we had multiple experiments with different numbers of threads and adjusting the ratio of operations. For each graph, x-axis represents a different number of threads, and y-axis represents the time to finish operations. Simply put, lower time means better performance. Blue, orange, green bars represent CrashLang, handwritten, and Memento, respectively. And as mentioned, we varied the ratio of operations for each experiment, and we are presenting one for each since different ratio of operations didn't change the graph drastically. Overall, CrashLang is slightly slower than the handwritten version for all three cases, and for the comparison with Memento for stack and queue, CrashLang is faster on average and significantly faster for linked list. We constructed CrashLang and its type system to help users implementing crash-consistent data structure using commit store pattern, and we proved that the data structure implementation is crash-consistent. We have implemented various crash-consistent data structures to show the usability of our language and evaluated the correctness and performance as well. There are more language supports in CrashLang that are not presented in this talk, and you can find more detail in our main paper, including more features and formalisms with the proof. That's all I have for today. Thank you.
Speaker. All right. So your next speaker. All right. So you can set up, and while people are thinking of questions. Oh yeah, sure. Go ahead. Yeah.
Sorry, real quick before I get mic'd. I noticed the techniques you're also. Hi, I'm Finn from UBC. I noticed the techniques you're showing and like the semantics are very similar to things I've seen people use in the multi-core like high-performance data structures community. It's not anything to do with crash consistency, but a lot of other lock-free synchronization, work stealing, etc. mechanisms. Would your work be applicable to this or related to it in some way?
Let's see. I know there are some lock-free data structure implementations that follows this commit store pattern. So yes, I believe if the implementation falls into this commit store pattern, then of course, yeah.
Thanks for the very nice talk. I was wondering, you generate Rust code in the end after you've used your type system. I wondered have you thought about, would there be some way that you could provide annotations on Rust code directly? So adapt your system to be able to integrate in some way with the type system that's already in Rust?
Yes, that was actually one of our reviewers' comment that, and yes, of course, we were also thinking to just implement this idea as like the additional type checker in Rust. Yeah.
Cool. Thanks.
Yeah.
I think we should swap the laptop. Yeah. Maybe as you're swapping. So for the helper function, what if the helper also crash? Does it like how do you make sure the helper's crash does not influence the rest of the behavior?
What do you mean?
So you have helper thread come back to finish the job, right? If it crash again, how do your proof apply to this scenario?
Maybe
it is offline now that.
Yeah, we can talk about it later. Thank you.